This is the introductory lecture for Chapter 14 on acids and bases. So there are two different definitions of acids and bases that we're going to concern ourselves with in this class. The first definition is the Arrhenius acid, Arrhenius base definition. And so the definition of an Arrhenius acid is a substance that dissociates in water to produce hydrogen ions, or this H+, sometimes we call that a proton. So you can see the general format of our acid here, HA, aqueous, is going to then dissociate to our H+ hydrogen ion and then the conjugate base. So we'll get to conjugate bases in the next slide, but we can see that is going to be your base of your acid. Okay, for example, if this was HCl, we would have H+ and we would have Cl-. Okay, so it's forming an anion there. An Arrhenius base is a substance that dissociates in water to produce hydroxide ions, or this OH-. So we can see here having a general format of a base where we have a metal with a hydroxide dissociating to form that cation, and we have our hydroxide here. And so a buildup of this H+. So it's important to know that in this lecture and in the upcoming few weeks when we're talking acid and base chemistry, we're going to use the hydrogen ion and the hydronium ion, the H3O+. We're going to use these terms interchangeably. Okay, so just kind of keep that in mind, that if we talk about a hydrogen ion, we're also talking about the hydronium ion. Okay, so that's just the hydrogen ion onto a water. So we need to remember that the buildup of these hydrogen ions or hydronium ions produce an acidic solution, and then buildup of the hydroxide anion produces basic solutions. So the second definition that we have here is the Bronsted-Lowry definition. So a Bronsted-Lowry acid is a substance that can transfer hydrogen ions, or the H+. In other words, it's a proton donor. Whereas a Bronsted-Lowry base is a substance that can accept hydrogen ions, or the H+. In other words, it's a proton acceptor. So if we have this reaction here, we have our acid here, and we can tell that this is the acid because it has this hydrogen, so that it can be a hydrogen donor or a proton donor. And then we have our other species here, which is our base, which is going to be our hydrogen acceptor. And we can see on the left-hand side, as we go over to the right-hand side, that our acid has donated its hydrogen, and it now forms what's called a conjugate base, where the conjugate acid-base pair are the chemical species whose formulas differ only by one hydrogen ion, or an H+. So we can see that HA here now turns into the A- anion. Okay, so that's a conjugate acid, conjugate base. For every conjugate acid, you have a conjugate base. And then, so over here, this is going to be our base because it's our hydrogen acceptor. We can see on the other side here, it's turned itself into the conjugate acid because it has now accepted that hydrogen. And we can see we've gone from a neutral species now to a positively charged species. So for every acid, there's a conjugate base. For every base, there's a conjugate acid. Okay? And the conjugate acid and base are separated by our reaction arrows. And so the strength of an acid or base depends on the extent to which it dissociates in water. So we have two different types of acids and bases that we're going to deal with. One is a strong acid, strong base, and the other is a weak acid or a weak base. So the difference is a strong acid or a strong base is an acid or base that completely dissociates in water and is thus a strong electrolyte. So if we see here a sort of schematic here, we have a concentration of a strong acid that's put into water. And then over here we can see the concentration at equilibrium. So remembering that we have our following the general format 2 slides back, showing that we have our dissociation of our acid into the hydrogen ion and our conjugate base. So going back up here, we can see that there is, for strong acids, there is no concentration, or basically practically zero concentration in that combined acid form, but that it is entirely dissociated into its H+ or H3O+. Remember, we're going to use those terms interchangeably. into the H plus and the conjugate base. Okay, so strong acids, strong bases have the same sort of idea here. We have complete dissociation into its elements. So whereas a weak acid or weak base only partially dissociates in water and is thus a weak electrolyte. So we have two different types of weak acids shown here. One that is just a moderately weak acid and one that's a very weak acid. So again, we have on the left-hand side, which is the concentration of the acid that we're putting in a water solution. And then here for the partially weak acid, we can see that there's partial dissociation. Most of the concentration still lies in that combined form, whereas only a small bit of it here has dissociated. Whereas a very weak acid, we can see that all of it is in the combined form and none of it has been dissociated, or little to no of it has been dissociated. So the relative strength of the acid, remember, depends on the concentration of this H3O plus or the H plus. So since as we go from the strong to moderately weak to very weak, we can see that the concentration of this H3O plus goes from large to medium to very small. So we can say that this is our strongest acid, middle, and our weakest acid. So in order to discuss this dissociation of acids or bases, we bring in the acid dissociation equilibrium constant, K sub A. Okay, and so we can see here that this is basically the same sort of idea as Kc that we talked about previously. Whereas we have our reaction here of an acid dissociating in water, so we have our acid plus water in equilibrium with its dissociated H3O plus hydronium ion and the conjugate base. Okay, and so what we have here, since water is this pure liquid, we're not going to include it in this equilibrium equation. So we have Ka is equal to the right side over the left side, or our air quotes products over air quotes reactants. So we can see here that this Ka term can basically tell us how strong an acid is. So the higher the Ka value, the larger the numerator and the smaller the denominator, which means the more that has been dissociated. Okay, so our strong acids are going to have extremely high Ka values, whereas weak acids are going to be held together in this combined form and not as much dissociated. So that would make the numerator smaller and it would make the denominator larger. So therefore Ka would be smaller for weak acids. And so the relative strength of various Ka or various weak acids depend on this Ka value. The smaller the Ka value, the weaker the acid. The larger the Ka value, the stronger the acid. Okay? And so you're going to hear us talking about ranking weak acids by relative strength. Okay, so we can rank which of the weak acids is weakest by which ones have the smallest Ka and which of the weak acids would be the strongest. The same sort of idea carries on to the bases. So we have a base reacting with water to form hydroxide and the conjugate acid. Okay, remember every base has a conjugate acid. Every acid has a conjugate base. So we can see looking in these last two slides that we have water when you dissolve an acid acts as a base, whereas water when you dissolve a base acts as an acid. So it's a very interesting sort of aspect to water that it can perform as both an acid or a base. And so remember that the amount of OH minus that we have buildup determines how basic a solution is. So if we look at our base dissociation equilibrium constant K sub B, we can see that the dissociated form is in the numerator, whereas the combined base form is in the denominator. So the same sort of idea. The larger the Ka value, the stronger the base. The lower the Ka value, the weaker the base. So strong bases, this Kb value is enormous because we have complete dissociation and basically none of this initial base. Whereas weak bases are going to have much smaller Kbs. So the same sort of idea, the same trends carry on from Ka to Kb. So here's just showing a list of acid-base strength, basically the extent of dissociation, as it's qualified by the Ka or Kb value. So here we're listing, in each one of these rows, we have a conjugate acid and its conjugate base. Okay, so we're going from the bottom on the left here are our weakest acids. To the top is our strongest acids. Okay, so these correspond to very low Kas for the weak acids and very high Kas for the strong acids. If we take a look over at the conjugate bases, we can see that the opposite trend occurs. That we have our strongest base. Oh, guys, there's a typo here. I'm sorry. So this high Kb here should actually say low Kb. And this low Kb here should say high. Sorry about that typo. Okay, so we can see here that the strongest acids give us our very weakest bases when you're talking the conjugate acid-base pair. So therefore, remember, we're scratching this out. This is a low Kb. Whereas our weakest acids here form our strongest bases, which give us, remember, we're scratching that out, to a high Kb. And so here's a table that actually shows the appropriate Ka values when we're ranking these acids in order of their strength. So as we go from our weak acid to our strongest acid, we can see that our Ka value goes from 10 to the minus 6, very small, 10 to the minus 10, minus 8, minus 5, minus 4, and then 10 to the positive 6, all the way for our strong acid, HCl. So we can see here, as the Ka value becomes larger, we will get a stronger acid. So right now you can disregard this pKa column. We'll get to that in future classes. And so the last concept that I'd like to go through today is the dissociation of water. So the dissociation of water exists at equilibrium. So remember that buildup of our hydrogen or hydronium produces an acidic solution, whereas buildup of the hydroxide anion produces a basic solution. And so we showed you before that water can act as an acid or a base depending on where you use it. But acid or water itself can dissociate. Okay, so you have two waters here reacting together. One is an acid, one is a base. And that water can dissociate to form H3O plus and OH minus. So we have the chemical equation written down here. And so the equilibrium associated, so remember, these are two liquid waters here, so those aren't going to show up in your equilibrium equation, but these two here would be aqueous, the H3O plus and the OH minus. So we have an ion product constant for water. So this is an equilibrium constant that's for water, K sub W. And that's going to be equal to the H3O plus times the OH minus. So those are just the air quotes products, or the right-hand side of this dissociation equation. Now, so this Kw value, this is a constant. This Kw value is a constant equal to 1.0 times 10 to the negative 14. And so it is equal to the concentration of the H3O plus and the OH minus in a solution. And so in a neutral solution, where we haven't added any additional acid or base, the concentrations of the H3O plus and the OH minus are both equal. And those would be 1.0 times 10 to the negative 7 molarity. So when you multiply those two together, you get to this constant. But one of the interesting things about this Kw constant is that it gives us a relationship between the concentration of the hydronium ion and the hydroxide anion. And we can see that these concentrations change together. In a neutral solution, the concentrations are both the same. Whereas in an acidic solution, the concentration of the H3O plus goes up and the concentration of the OH minus goes down. Whereas in a basic solution, the concentration of the OH minus goes up and the H3O plus goes down. So you can see that these changes are compensatory. They go together. And they relate to this constant of the 1.0 times 10 to the negative 14 that's equal to Kw. So if you know either the concentration of H3O plus or the concentration of OH minus, you can determine what the concentration of the other ion is, because this Kw value is always equal to 1.0 times 10 to the negative 14 at this 25 degrees Celsius mark. Okay, and so this is just saying the last thing that I just said there, that Kw can be used to convert between concentrations of H3O plus and OH minus. All right, so this gives you the proper preparation to work through that acid, base, and Ka worksheet. So there are 2 worksheets that you should complete here, and so please have those worksheets totally finished, and you can bring any questions to class with you for Friday the 14th of February. Okay, thank you, and we'll see you tomorrow.